electrostatics sheet out. We're going to go through really quickly the top of it just to make sure that we're all on the same page, okay? And then we're going to move to the bottom of it, and then you're going to go ahead and work on the back of it. It'll just be a great day, just like that. It's exactly how it's going to go. All right. Good. There it is. All right, here we go. Static electricity basics. We're going to go one person at a time. Kate's going to be first. Are you ready, Kate? I'm going to read, and then you fill in the blank. What's that? Oh, that's the one you didn't get? All right, then Ellie can go first.
It might be electrons. We work together.
Oh, okay. We'll start with Harrison. Is that okay? Then we'll go back that way. It'll be beautiful. All right. I didn't mean to stress you out. I'm sorry. All right. Number one, or the first check mark says, an object or surface's net charge is due to an abundance or lack of?
Electrons.
It is. And to be clear, I get lazy really fast, and so I write my electron like that. And if you don't do that, then just know that that's how I do it. All right, and if an object or surface has an abundance of electrons, it has a negative charge. On the other hand, if an object or surface is lacking electrons, it has a... Indeed. That was Ellie, sorry.
We're snatching it back.
Are we okay? Yeah, we'll come back. I'm sorry. Aiden you were really excited about that one, weren't you? I'm sorry. All right, friends. Shh. Here we go. If two objects with like charges are brought close to one another, they will, Kate? They will. If objects with opposite charges are brought close to one another, they will? Okay. When charging an object within a closed system, if one object gains a given number of electrons, the other one must lose the same number. Or the same amount. Either way is good. This is due to... Aiden, do you want this one? Uh-huh. Now you got a double because you got that one, right?
Yeah.
Awesome. Okay. Moving down. In terms of electricity, materials are said to be either... Jacob? Or insulators within... Where are we going next, Nick? Conducting or conductive. Materials, electrons are able to move freely or be charged easily. Jonathan, did you guys get any examples of conductive materials? No? Henry's got this one. Go. Pickles. I'm going to honestly say that in my more than 15 years of teaching, you're the first person to say pickles for this space in this thing. And I've been using this for a long time. So well done.
Thank you.
All right. I mean, it's not wrong, but it's just the first time I've ever written that down there. Tate, do you have any more? Metal. Some metals. Many metals. And Isaac, do you have one more? No? Anybody else have one more? Water. In particular, what kind of water?
Tap water.
Tap water.
Pool water.
Non-distilled water. Yes. Gatorade is a good conductor as well. Yes. All right.
Wait, you didn't put Rudy.
I didn't, because I don't have time to waste doing lots and lots. But yes. Within materials known as insulators, what do those electrons do, Cole?
They move less freely.
They move less freely. Or they are stuck in place-ish. All right, examples of these insulators include, what, Idris, did you have any? Plastic. What else was on? Paper. Friends, I don't know why it's so hard to ask you to be quiet today. I don't know for sure if there's something else going on in the world, if the moon is full or what, but I've asked you a lot of times. So either be quiet or move somewhere so that you can be quiet. Okay? Okay? Yeah? Okay. All right. Plastic, paper. Lexi, did you have any other ones? Those two. Anybody else got another one to add to the list? Go. Oil. Others? Rubber. Distilled water. What's the difference between distilled water and tap water, distilled water, and any other kind of water? What's special about distilled water? It's just water, right? Any other water has got other minerals in it. Those minerals are the things that are actually really good at conducting electricity. All right, here we go. Transferring charge. I don't know where we're at here. Let's see. Lexi, I think that we are there. Do you have this one? Or no? Okay. This one, I didn't know how far we got on this. How far did we get? Are we ready? Somebody want to do it? There are two ways to transfer charge, contact and
Induction.
it is induction. It's they are called contact and induction. That's how they are defined generally when we're talking about electrostatics. In the case of contact, what's this word here? Blank actually move from one object to another. Electrons actually move from one object to another, causing both objects to share in the abundance or lack thereof. In the other, induction, that one was pretty easy. Induction charges objects without touching them. This is the one that you are much less familiar with, likely. Okay? Most people have not seen this one or seen demonstrated this one, so we're going to do this real quick in just a sec here. Okay? For example, if a positively charged rod is brought near an uncharged metal body mounted on an insulating stand, free electrons in the metal are what? Electrons are what? The positively charged rod. Are they going to be attracted or repelled? Attracted. Yeah. Okay, you guys need to move. The three of you need to not be sitting next to each other right now. And I'm not upset. I just need you to move because I can't handle it. So please move. Thank you. Free electrons are attracted to the positively charged rod, okay? Leaving an excess of what? The electrons move. What's left? Protons, positively charged stuff, right? All right, I'm going to show you this real quick. I'm going to try this with the document here. I've never tried this before, so we'll see how this goes. All right. Just a second. Freeze that. Pause this. Let's flip it over. I'm going to give you a little push in the right direction on the back, and then I'm going to let you get started. Okay? So on the back, we are now going to quantify the force that causes those two little pieces of metal to want to get away from each other or come back to each other, okay? The relative attraction or repulsion of two charged objects is caused by the, does anybody know what this force is called? The electrostatic force. It's quantified using Coulombs Law. Oops, let's see if I can spell it. C-O-U, here, I'll write it out really nicely. C-O-U-L-O-M-B'(S). Coulombs Law. I don't know any dirt about Coulomb. I kind of wish I did because I feel like there's got to be a story in there. I've never researched it, so it's not that he's totally clean. I just don't know anything about him. Okay? He did kind of hit the jackpot with this thing because everything in this law is named Coulomb, which makes it really easy to remember things, which is kind of nice. Coulomb's law includes two primary variables for the force. The first one is charge. So you might want to underline that or highlight that or circle that so you know that the first thing that we care about is charge, okay? And because we like to make things logical, charge is marked with the letter Q. Okay? Sometimes it's a big Q and sometimes it's a little q. And they use them interchangeably. There is not really a good reason for big Q versus little q, although what I've noticed is that generally big Q is used for things that are bigger charges. But there's no really good reason, and there's no really good rhyme or reason to it, okay? And charge is measured in, you guessed it, coulombs, okay? So Coulombs law includes charge, which is measured in coulombs. If the charge of one or both objects increases, the force of attraction or repulsion will be what? What do you think? The bigger the charge, the bigger the force, or the smaller the force?
Bigger.
The bigger the force, yeah. What evidence do you have for that, besides just a gut feeling? Have you ever experienced the Coulomb force before?
Yeah.
Yes, when?
I
No, wrong answer. Good guess, wrong answer. It's not actually magnets.
occasionally I set up two parallel wires and run them down through each.
I'm sure you do. You have all experienced this. You all experienced it this summer, or not summer, excuse me, this winter, with your socks, right? And the carpet, and your little brother, right? Okay? That is the Coulomb force. You understand what I'm saying?
Yeah.
And it might not have been your little brother, and it might just have been you when you went to turn the light off. Okay? But it has happened to you, I am sure. Okay? In any of those cases, friends, the more that you rub your socks against the carpet, the more charges that you've ripped off, the bigger the shock will be. And it'll be the bigger to you and to your little brother or whomever experienced it, right? Okay? That is the evidence that you have for that. More charge, bigger force. The other thing that it is dependent on is distance. Marked sometimes with an R, sometimes with a D. Okay? It is now your job to investigate how force and distance are related. So I've given you some data, some relative separations. They don't have units, and I don't want you to worry about the units. It could be centimeters, could be millimeters, could be who knows. And I've got forces. Could be newtons, could be kilonewtons, could be micronewtons. It doesn't matter. But I've got separations and I've got forces. And my task for you right now in the next 5 minutes or so is to try out two different relationships between these data points. Even if you have a gut feeling, I want you to look at it and think about it and see how it works. Okay? Your goal is to make it fit a straight line. Surprise, surprise. We're trying to make it fit a straight line. Okay? Work with each other. Grab a calculator. You'll probably need one. Once you've got it, let me know, and I'll get you those notes for Coulombs Law. Okay? It's up to you to figure it out. Work with your partner. Work with your partners. Find somebody to work with and do it. So, friends, spoiler alert. I need to tell you the answer to make sure that you're good to do the homework that I just handed you, because we've got to keep cruising, okay? So many of you are on the right track, and I still want you to go through and do the graph, okay? I still want you to go through and do the graph. The proportionality that we're looking for is that F is proportional to Q1, Q2 over R squared. Oops, that's frozen, so you can't see what I just wrote. Ha-ha. It's a 1 over R squared thing, just like gravity. It's beautiful and wonderful and great. Remember, gravity was Fg is equal to gmm over R squared. And the electrostatic force is kqqq over R squared. They're very, very similar. Make sure that you write this down and this down before you go. I just gave you a half sheet of paper. This is your homework for tonight. I want you to have this done when you come into class tomorrow so that we can talk about this and move forward with this tomorrow, okay? Friendly reminder that Thursday we have a test over this stuff, right? Yeah. We'll make it Thursday. We may kind of wiggle around. I feel like Thursday would be better than Wednesday, though. Do you guys think? Yeah. Okay, we'll do it Thursday. That's what I'm thinking. All right, my friends. Have a fantastic day. I'll see you tomorrow.
Like, it's a little bit.